Hello and welcome back to Let's Code Physics. I'm real excited to share today's episode with you because I did not expect to get the code to work today. I just expected to kind of give some updates about it. So you'll see me kind of starting out kind of buried into the code. Then I go away and come back and go away and come back because I'm letting it run. But what you see here is the beautiful results. We have our Gaussian remaining a Gaussian in the harmonic oscillator potential, and we have the expectation value behaving kind of like a sine curve. Kind of like a cosine curve, excuse me. Yeah, it's heading towards 0 right now, so it's about to cross through the axis. So it's going to be really cool. So thank you so much for watching, and I'll see you in just a bit. It's Tuesday, April 5th. I have continued to look at the wave function evolver. I've tried simplifying my life by making my initial wave function flat, so it's completely flat along the entire plane that we're looking at, or along the entire region of the plane that we're looking at. Potential energy is still 0, so this thing should spread out into some sinusoidal waves. I still get the same issue. Let's run the code and I'll show you. Still it has this little ripple that's spreading in from the left, and what you can see is it's like it's being pulled down to this part, which I would kind of expect because this outer edge here, this boundary condition, is kept at 0, and so I would expect that to kind of snap it there, but I would also expect it to do that on every side. I mean, that's the entire point of the code, is to treat it like it's got infinite barriers there. And so I'm not really sure what's going on with that. And the reason I'm really not sure is because the same thing should be happening on the right side, the bottom side, and the top side, and they're not even moving. I mean, I can't really tell that they're moving, at least not noticeable compared to that. And here's how I am pretty sure it's an artifact of the code, is I rearranged the way that my X-array is set up. So this now starts X at the maximum X and decreases it each time when it's setting that up. And now that disturbance comes in from the right side. So I'm pretty sure that means that this is some sort of error with the loop itself, with the way I have the loop set up. Now what you do notice though is that there is some fringe effects. There are some fringe effects happening there at the top and the bottom. So maybe it is actually pulling it down at the top and the bottom. I suppose another thing I could try would be to see what happens if I make psi initial be 1 only if it's, say, within a certain range. So like let's take that region and only take the middle of it. So let's try if x is less than 0.5 and y is less than 0.5. Actually, let's make that absolute value, shouldn't we? So now let's just do a 1 by 1 square inside the larger 2 by 2 square. So if it's within that, make psi initial equal to 1, and otherwise make psi initial equal to 0. Let's see what happens there. Where did it go? Okay, it's up there. Oh, and now it's actually working. That's more of what I would expect. Okay. Huh. I wonder if the issue is that the boundary was just too thin. I mean, there's still oh no, I have it set up to where the problem will be on the right side. That is, I was going to say there's a little bit of asymmetry there, but there's a little bit of asymmetry there too. How far out can I push that? I also decrease my dx, or my nx, increase my dx in order to make the code run a little bit faster without running into issues. Okay. So maybe I need a thicker boundary? Did that work? All right, let's see here. Let's see, file, save as. Let me just save this under a different name. This one was somewhat working. Let's call it maybe working. Maybe is better than somewhat, right? maybe implies at least somewhat, right? All right, let's try increasing our nx. Let's put that up to 40. Let's leave the dt the same. So my epsilon is still 10 to the minus 3. Still maintaining its symmetry. So in other words, what if I just need to keep more data points around here flat? Because that's progressing symmetrically. Okay. Okay. Can I increase the dt a little bit? Maybe increase it by a factor of 10. So now it's 4 times 10 to the minus 2. I think I can decrease the psi factor there. That's kind of cool. But it's symmetric. It's not showing that rippling in from the outside. Okay. All right. With that, then actually, I think I want dt. Let's go. Let's turn that 5 into a 1. I feel like I need to compromise between those two. Okay, I think that's working now. Cool. All right. Well, excuse me. It solved the problem for that wave function. Let's try the displaced Gaussian now. 3, delete. All right, let's try the displaced Gaussian now. Well, I'm not. Oh, there comes the ripple. Okay, so I got it working better for one of them. Oh, I didn't put in the, oh, silly Brian. I didn't put in the if then. Excuse me. Sorry. I just completely undid what I did, didn't I? Let's see here. Let's try this thing. Oops, a little too much indent. A little too much. There we go. F5. Okay. All right. I'm getting raises on all 4 sides now, so that's good. Okay, so for whatever reason, the way that loop was set up was just favoring one of the sides. I'll see if I can go back and actually figure out how, but the important thing is I've got a Gaussian now. So in the infinite square weld potential energy, the Gaussian is not going to remain a Gaussian, right? It's going to break up into sinusoidal components. So let's now turn on the harmonic oscillator potential. So this is a harmonic oscillator in both the x and the y directions. I know you can tell my 3-dimensional gesturing with my cursor there. It's now in a harmonic oscillator in the x direction and in the y direction. There, wasn't that better? So this thing should, if this is working correctly, remain a Gaussian. Well, it's not rippling in from one side. That's not really what I would expect. So I don't think this is correct quite yet, because this Gaussian should remain a Gaussian. It should go back and forth as a Gaussian in the harmonic oscillator. Except it's not really Gaussian because I have the outer parts of it flattened. What if I change my x-min and x-max? What if I make the square? The square is not going to appear larger, but it's going to take up a large amount of space. Oh, what did that do? Oh, this needs to be a multiple of x-min and x-max, excuse me. So let's grab all of these. Let's grab all those, put those before that. There we go, because I need to have x-min and x-max defined before I do this. So this needs to be times X max. There we go. 0.75 times y max. There we go. That'll be better. Okay, that is a better looking Gaussian because now, now we're actually in the concave down portion. Oh, was this my problem all along? Was that or part of the problem was that I didn't have enough of a spread to the function? So that thing is staying as a Gaussian, though I wouldn't expect that. I would expect it to move back and forth along the x direction, because it's like you've taken the spring and stretched it along the x direction, but I guess I haven't stretched it very much. I guess it's adjusting a little bit. Let's try straight. Oh, I've only stretched it by 0.025. Let's try stretching it by 0.2. So 10% of x max. Because it should be moving back and forth around here like it did in the one-dimensional case. That is moving, isn't it? I don't know. I need to find another chair. Sorry for that pop. Not that I don't like this chair. I've had it since college, which is a sign that I like this chair. Also a sign I should probably get rid of it. Let's see here. What could I do? Let's stretch it out a little bit more. Let's stretch it halfway to the maximum. That doesn't look like that peak has been displaced by 1. I mean, I guess so, because that goes out to 2. I do have another chair. It's just not as comfortable. Let's see. This is supposed to go back and forth like a. Here, let's try displacing both of them. Same amount, so it'll appear kind of diagonally off from the center now. Does not appear to want to move. Okay, let's double check something here. Let's try something that I know is not a stationary state. Let's go back to 1 again. Let's go back to flat. Okay, good. So the code does move forward. Okay, well that's good to know. And this is under the x squared plus y squared potential energy. Although that potential energy, it should have some kind of spherical symmetry to it. Oh, what's going on with that? Why has this lifted up so much? Did I miss something? Oh, this edge is not glued down. Why is that edge not glued down? If absolute value of x is less than that, and absolute value of y is less than... Oh, I never changed that one. Oh, excuse me, I never changed this one. Oh, I don't want to make it 1. I want to make it... Sorry. That might explain part of it. Okay, well, there we go. The xy symmetry is back now. Okay. Let's try another one. Let's try sine of pi x times sine of pi y. Yeah. Because this is definitely not a stationary state of x squared plus y squared. And it is changing. I would like to see these changing a bit. Yeah, you can see the sine curve rising there. Okay. Okay, so that's making me feel better. Hash, okay, unhash. Zoom out. Because I would expect this thing to be springing back and forth. Maybe I need a stronger potential energy. Let's try putting that as 10 times this. So that would make the spring stronger, which should make it pull faster. The reason I definitely want to get this problem settled is because this is the quintessential problem in physics. This is the one that you test against any new method of solution or theory or something. You say, well, go try it on the harmonic oscillator. It's moving slightly. Okay, tell you what, I'm going to call this a mark of progress. What I'm going to do is I'm going to set this up to give me the expectation value of x, and I'm going to run this for about an hour and see what happens, and I will hopefully have something to show you. So the code has been running for probably about 10 minutes or so. It ended up not needing to run an entire hour, so I'm adding this on at the end of the video. Oh, wait, I don't want to introduce like that. Excuse me. So the code has been running for about 10 minutes now. It has roughly maintained its Gaussian shape. There's a little bit of a dip going on there, so that shows you some imperfection in the approximation technique. But it has moved. The center of the wave function has moved to where this is the expectation value of x, and it is decreasing a bit. And it's you know, it's kind of sinusoidal shaped, like you might expect. It's concave. It's roughly concave down. It's got a few dips right there. So that's encouraging to see. I'm going to continue to let this thing run and see what becomes of it. This thing is actually behaving the way you would expect because it's getting narrower and taller as it gets closer to 0, and our expectation value is almost 0. So this thing has been running for several minutes now, probably on the order of like 20 minutes or so. The peak is almost over the origin. It's almost over x equals 0, y equals 0. So one of the things I'm going to do off camera is I'll add in a code aligned to make the color different along the y-axis and along the x-axis, y-axis and x-axis, so you can tell where they are and where the origin is. The expectation value is behaving pretty much like you would expect. It is being pulled in towards 0, and it's accelerating as it goes that way. I mean, it's kind of flattened out here, so it's kind of sinusoidal-ish, like you would expect from the one-dimensional problem. The Gaussian peak itself is behaving like you would expect because if you remember in the one-dimensional problem, it gets wider when it's out toward the edge and narrower when it gets into the middle. So that's pretty cool. So I'm going to call this one a success. This thing is working pretty well. I think I have fixed the issue, at least for the problems we're considering now. So what I'm going to do when I make the next video is I'll go ahead and get it set up, and then I will let it run for, you know, a couple of hours so that there's something interesting to see about it, so that we don't just have to, you know, look at the first the first couple of just the first couple hundred iterations. We can look at a nice complete cycle. So there will be a little bit of splicing to do there that might cause the next video to be delayed. I'm not sure. But anyway, thank you so much for watching. I will see you next time. Bye-bye.